Alrighty, I think we're good to go here. I had an internet outage last week. I saw too. That was rough. So that would have been really hard to stream from class here. All right, so we got a couple things today. We'll get to our heaps in a little bit. Oh no, second page here. Sorry. So we'll get to priority queues in a little while. I think today we'll finish out talking about positional trees and then the positional linked list from the lab last week. I had some other questions about that as well that we wanted to get working on. So let's actually do that positional list first. This was our linked list. So what we wanted to do was add this idea of the positional wrapper to our list here. So that way we could, given a position, add and remove from it instead of having to go find a particular index. Right, so we could add something at a given index if we wanted, or pop from a given index. But it's slow to go find that index is the problem. So what we can do is we can use positions to say, hey, this is where I currently am. Now, if I'm already here, I can add before and after it really quickly. And that's that idea with the position wrapper. So I think starting with the circular doubly linked list was probably the easy route to go for that, to add in that position wrapper. And then we were going to add new features and functions to that. So let me go find that lab real quick. I don't remember if I listed them out or if I just said what page it was on for lab 5. Oh no, 6, sorry, our linked list here. Yeah, so this so from a list, give you the first position, from a list, give you the last position, from a list, give you what comes before a given position, what comes after a given position, whether or not it's empty, the length of the list, and an iterator for a list. Are there ways we can get positions out? And then these are ways we can interact with them. So I can add an element as the first item. I can add an element as the last item. I can add something before a position or add after a position. Or I could replace the value at a position, or I could delete a position. This was sort of that idea using that positional linked list here. Let me go grab, I think we just shamelessly copy pasted the position portion out of the textbook, which was fine. I think I've got, yeah, this one here. We'll just go find his and copy paste it in to make our positional list. So I'll just copy paste and start editing things as we go. I find that is a little bit easier than trying to do all the inheritance stuff. We'll make this our positional linked list here. I'll zoom that in a little bit, sorry. And all right, so we're going to go to our linked lists here, and this was the positional one, positional list ADT. So this was the position class here. So we're not going to bother with the inheritance portion of it. We can just say, hey, this is the position here then, and we have some little helper methods for validating given positions. And none of this copy pastes in nicely, which is a little bit unfortunate, but we'll make it work. So we'll go, maybe we'll put it all here at the top. Probably doesn't matter where. Let's see, oh goodness. That's a really ugly copy paste. Hang on, maybe if we put it in Notepad first. Maybe. Nope. All right, we'll do it little by little then. So, init. This was a class for the position, and it had an init, given a container and a node. So the idea with a position is the container is what list does this belong to? And then what node is this position pointing to? So position is a wrapper around a node that also knows what list it belongs to. We can make these positions from our instance of our linked list here, given a container and a node. Yes, it's probably easier. That's fine. We can copy out of here. And then getting out the actual data itself, right? It gets the node element. We can define an element method. Did we do element on the other ones? I don't remember if we did or not for nodes. Excuse me. I think I called it data. I like data rather than element. Data. Hector, my friend, thank you so much for donating those bits to the Student Scholarship Fund over at the University of Michigan Dearborn College of Engineering and Computer Science. I got it in one breath. Tomorrow is Giving Blue Day, apparently. So tomorrow we'll be making a donation and hopefully getting in on some of those challenge matches here. So I'm pretty excited for that. So the data, then, if you want to get the data out, is going to return self.node.data. Because we just take the node that we're storing and return that data from it here. So node has its data here in our circular list. So you can get the data out, and then if one is equal to another, we can return those ones. That one's pretty straightforward. All their comments are, I don't know, maybe they're helpful. So it's comparing, hey, are we the same here? We're the same type, and our nodes equal. So if two positions point to the same node, the positions are equal. So we're not saying, are you the same position in memory? Because you can have two different positions. Like if I started at the front with a position and started at the back with a position and started moving, eventually I'll get two different positions that point to the same node. They should be equal, but it won't be the same position in memory, but they're pointing to the same node in memory, is why we're comparing these ones here. And then not equal is just return not self equal other, right? We already know how to do equal, so we just do the opposite of that. That one's pretty handy. Oh, I guess the parentheses here are nice, right? Yeah, so type is this position. It's positional linked list dot position because it's a class inside of a class for the type. Yep, and then validate here. This one is actually very useful here. It does a lot of interesting stuff. So validate is how do we say, is this a valid position? This is the one that copies terribly. There's a type error. Sure, we don't actually really care what the type error says. That's okay. And then if it's not self, we're going to raise a value error. Yeah, that's fine. Sorry, the copy pasting here is ugly. We have a way to indicate that it is not ours. Okay. Is that all? That's probably a fine comment. I don't know why that's highlighted funny there. So we're going to say if it's not a position, it's invalid. It's not a valid position. It's the wrong type here. If the container is not my list here, it's no good. I'm sorry, so validate is part of the positional linked list class. We're validating a position. If the position is the position class, good, that's the right type. If the container is itself, so this instance of the positional list, does the position know me as the container? Great. And then we can say the node's next is none, is our way of saying this node is no longer valid here. Otherwise, we'll give you back the node. So we do a couple steps to validate a given position here. Okay, so now we have the position wrapper. I think that's pretty good. Now we need to go and add one other helper, the make position here as well. Take our make position. So another way, so given a node, I can turn it into a position. Oh, it didn't copy. That was the wrong copy. Make position. Copy that one. There we go. For a given node. Did not copy everything. Ah. So if it is our start node here, we're going to return none. If they gave us the starting one, oh, make position, there we go. If they gave us the starting node here, right, we're going to give them back none. It's not a valid position. Otherwise, we're going to return a position, so self.position, given self as the container and the node, right, as the node. So as long as it's not our starting one, which is that circular link for us here, we'll turn the node then, we'll wrap it as a position. We can return that. So those are pretty straightforward, I think. Right, and then first self, we can do all these other ones here. So these ones we won't need to copy paste. Okay. So then to add in our first or last, before and after, and we start going through these. So to get the first position then, so define first, here we're going to return self.makePosition given self.starts next. Right? Self-start is the start of our circular doubly linked list. Its next is always the first thing. If it points to itself because it's empty, then you're going to get back none. There is no position to give you. So this kind of fixes it. And this is why the position or the circular piece here is super nice, because we always have a next. And then define last, return self.makePosition of our starts previous. Oops. Previous. Right? The thing that comes before our start is the end of the circle. It's either the last thing or itself if it's empty. So then we can define, let's do after, given a position. So what comes after a position? Well, first we need to validate that position to get the node out. Right? We're going to make sure it is a proper position here. So we're going to say the node is validate, self.validate the position. We should get a node back out. Right? It probably, if it crashed, it crashes, and we're just going to have to deal with that. But otherwise, we get a node back out, and then we can return self.makePosition of the node. And I'm sorry, makePosition should probably be a private. These should be private helper methods here. We don't want public access for these. Just to make this a little cleaner here. Right? We don't want other people using these functions. We'll just mark them as private here. So to get what comes after a node, given a position, validate the position, get the node out that it was pointing to, and then take the thing that comes after it. Oh, sorry, node.next. Right? Take the node next. Now we have the next position in our linked list. Same thing with before. So before a given position, we just take the node's previous. Right, what came before me? Okay, well, let's turn you into a node and take the previous link off that node. Okay, so we have first, we have last, we have before, we have after. I think we already have isEmpty list. We already have our isEmpty. I think we do. Get item, set item, insert, pop, remove. Yeah, we have isEmpty, we have length. So we don't have the iterator yet. So the iterator piece is what we're missing here. Now this one's probably fine to copy paste, our iterator. So this will make life pretty easy. Here, we're just going to start at the first thing. And we keep going until we run out. So I like current as first, as long as we're not none, right? Because we get back none once we finally hit the end. We're going to yield the current data, because we called it data, right, for our function here. Then we're going to move to the next one, self.after the current. What comes next? Right? Eventually, self.after will give me a node. Right? The node's next is going to be that starter node, right? Because we've come full circle once we've gone all the way around. Then when we go and make position out of it here, we're going to give back a none. Our loop only works while current is not none. So the loop will stop, will no longer yield any data. So it's a quick way to iterate over our linked list here. So we can use it in a for loop now. And say for value in positionally linked list, because I have an iterator. We're just going to current. That's right, current. Current is what comes after the current. That's our iterator. Length, great. So now we need to do the add first, add last, add before, add after, replace, and delete. Sure, we can do all these. So adding first, adding last. Those are nice and easy. I think we do even have those already in here. Let's see. Don't remember. We have append, which is add last, right? And then do we have an add first? We have an insert. We have a validate index. This should be a helper method too. That's my mistake. We have pop, we have remove. Okay, so we need to add first. We can do that. So if we want a add first. Assign add first here, given some data. Well, we're going to add a node. Right? Remember, we have this helper function for add node that knows what comes after it and what comes before it. So if we're going to be the first thing here, we're going to add a node. If it's the first thing, what comes after it is self-starts next, and what comes before it is self-start. Right, this is the previous, is the start of our circle, and what comes after it is what used to come after it, and then we'll fix it up itself with adding first. So append is essentially also add last, and this then is also, right, O of 1, always constant time for our performance. Fantastic. And so, okay, so we can add first, we can add last. Now we can add before or add after. So these ones are a little bit trickier, but not too bad. So to add before or add after, add before, given a position. Right, well, first we're going to validate it. So we'll have the node is self.validate the position. Now I know what node it points to. Then if I'm going to add before this one, I'm going to call self.addNode. I'm going to add the, oh, I'm sorry, we also need the data, right? I forgot. So the position and the data. We're going to add the data. What comes after it is the node. What comes before it is the node.previous. Right, we're going to go in between what comes before what we're pointed at, and this thing will come after us. Same with add after a given position. Oops, those are tabbed too much. So for adding after, we'll validate. And then what comes after us then is the node's next. What comes before us is the node. Right? The node that this position looked at will come before us. The thing that comes after us is what used to come after it. And then we'll fix ourselves up in the list. Sorry, the chair is funny here. Okay, add after, replace. So we can replace a given value. We don't actually have an update, do we? We have a set item. Set item essentially does that, right? But it needs an index. So we want to be able to set something given a position here. We'll define replace given a position and the data. So we'll validate, get the node back out. And then we'll have the old value is node.data. Or I don't know, old data, sure. And then we'll say node.data is equal to the data we were given, and then we can return the old data. Right, validate the position, grab the old thing, update it with the new thing, and then return the old thing. It's just common that replace will usually give you back the old values. It's your one last chance to go grab it here. I think we did that with our sets too, right? Yeah, we returned the old data. Same idea here. But now we don't have to go walk to it. We have the position already, so it's a constant time operation. So all of these here then are O of 1, because there's no walking. We already know the position. So it doesn't matter if I've got a million things on my list. I can replace the 700,000th one if I already have the position. Right? Same with add. If I add after, if I already know the position, I can add after it in constant time. I can add before it in constant time. So lists that are going to be changing a lot of values back and forth are very quickly done as linked lists if we can get to the position and stay close to that position. So if I've got a list of 100,000 things and I'm like going from the front to the back to the front to the back to the front to the back, it's not going to be very quick. Again, you can do other fun things where you can kind of keep more positions in memory. And we can say, oh, sure, okay, so this position is 2/3 of the way in. So if your index is anywhere within some range of that, I can start here. So there's things we can do to trade off memory to store positions to make things faster if we already are close to given positions. So we got lots of fun things. Hey, my friend Y Paladin, thanks so much for coming on by. Appreciate it, my friend. A DevOps folk. I think you're in the DevOps family, right? Out on the West Coast. So it's always fun making friends here on Twitch land. All right. So the last thing then is delete a position. Okay, so we have to go delete the position. So to delete a given position, fine. Was this remove or was it delete? I think it was delete, given a position. So we have a remove helper, right? I think we have a remove helper. Yeah, we have a remove node. We can remove a node, right? And that will set the pointers to itself. Oh no, it doesn't. No one never cleaned it up, did it? So we should set those, because one of our conventions here for validating was that, where was it in here? Its next is none. So if the node's next is none, we know a bad thing happened, because we're a circular list. It should never, ever, ever be none. So what we want to do then, a system cutover planning. All right, have fun with that, my friend. So when we remove the node, we should set node.next is none, and we can set node.previous is none. Kind of clear those out, and these will indicate to us that this node is no longer valid. Okay, and then we can give you back the data. So to remove a position, delete a position, right, we need to go validate it first. Go get the valid node that it points at, right, and then we're going to return self.remove node given the node. That will give back the data, right? Remove the node out of the linked list, and everything happens. So not too bad to add those in here. Again, I didn't do the inheritance thing. It would have been probably just as easy to do the inheritance, right, if we inherited from our doubly linked list, but this way you kind of see it all here at once. I kind of like that a little bit better, just for following along here. So yeah, and deleting, again, is, you guessed it, O of 1. O of 1. You guys are good guessers of this. Thinking all these things are constant time operations, right? Because once we know the position, linked list operations happen like that. It's getting to a position that is slow with the linked list. Okay, and then what we wanted to do with this here is we wanted to say, okay, let's go, what do we have to do? Ask for user to enter some names. We're going to insert them into sorted order in the list, then print them all out. Okay, sure. So we'll say, how about a name is nothing, and while name does not equal stop or something, we can say name equals an input of enter a name or stop to stop. I think stop is pretty clear what that means here. And then we'll take that list. We need a positionally linked list here. So our linked list equals our positional linked list. We'll take our linked list and we will, we need to put it in sorted order. We need to go find where it goes. So the very first name, we know it's empty. That one's pretty easy. So we can say, hey, if the length, or we'll say our linked list dot is empty, our linked list dot append, we can just append the name. That's the easy case, right? It'll only work once. Otherwise, well, what do we have to do? We have to see, is it going to go before or after? Right, so then we're going to have the current is my linked list first. Start there. Then we can say, hey, if the name is less than the current dot data, right, get the data out. If we're less than, we're going to be before alphabetically, which is a little funny, but it's okay. Then we can take our linked list dot add before the current. And what do we need to add before? We need to add the name. So if your name is Eric, and then I'm going to add Anne. Anne is less than Eric because A is less than E. Because remember, use those numeric values. It's sort of silly here. Don't worry too much about the numeric sorting here. We can add it before. If it's not less than, right? Well, we need to keep on moving then. So really, this is while, I don't know, this. If it is less than, we add it. If it's not less than, then we want to move to the next node. So kind of want this to go until we get it to be less than, right? So let's say while name is greater than, we'll say current equals my linked list dot after current. So if I'm greater than you, let's move to the next one. If I'm greater than you, let's move to the next one. If I'm greater than you, move to the next one. If I'm greater than you, move to the next one. Now the problem is, eventually one of these things is, if I get all the way around the circle and I get to none because I'm greater than all the names and I am the greater, I'm Z, and I'm going to be at the end here. If there was no other Z, my after is going to give me back a none. So then I need to check, before I go add that, I can say, hey, if current is none, then we want to take my linked list dot add last. Then it add last, linked list dot last. No? Append. That's right. I didn't change the name of it. Thank you. Append the name. Otherwise, then we can say, okay, let's add it before the thing that's current, because we were no longer greater. Right? If we're no longer greater, then we need to come before that thing. I think this will work for us. We'll try it and see. Right? And that ought to do it. Right? If we're empty, add it to the beginning. If we got to the end, add it at the end. Otherwise, add it before the thing that we are less than. Because as soon as we become less than something, our loop will stop here. Let's try it and see. And then we just keep on going here, right? Add a name or stop. So, okay, so if name does not equal stop, then we do this thing. That's a little bit ugly here, but that's okay. I don't know, it'll probably work. Should we try it? Oh, and then we need to print them all out, so we can say for name in linked list, print name. These are positions, so it's actually, this will be position, right? Position in linked list, we'll say position.data, right? Because we can iterate over using that iterator we wrote. Will give me positions out. Where'd that go? Our iterator. Iterator, right? We'll give the, oh no, we're yielding the data. I'm sorry, we are yielding the data. You just print name and for name. Name, print the name. Let's try it and see. So let's add Eric, and then we'll add Bob. Should come before Eric. Uh-oh. We broke it. We can't make a position out of self? Self.position. Oh, I spelled it wrong. I said poston instead of position. Postion. There we go. Okay, that was just a typo. Try it again. We'll add Eric. We'll add Bob. We'll add Carol. It should be in the middle. Zed should be at the end. Uh-oh. None has no data. Okay, so while current does not equal none, and so if it does equal none, then this is false and the loop will stop. Sorry, is not none, right? Because we can't get the data out once we hit none. Let's try it again. So Eric and Bob and Carol and Zed and stop. Do we get Bob, Carol, Eric, and Zed? I think the cases worked here, right? We tried something before, we tried something in the middle, and we tried something at the end. So just in terms of thinking through, did we hit all of these different conditions here? It's not a proper unit test, I'm sorry. We're eyeballing it here. We're being bad. It'd be better to do a unit test for this sort of thing, but again, we're just exploring. Does that make sense what we're doing in the lab then for that one? Okay, cool. Then we're doing the same idea with positions and trees. Oops, not zoom out, zoom in. There we go. So we had our binary tree here of type tree. Right, so we're extending tree. Oh, no. Why is it unhappy? Expected 2 blank lines, found 1. One more? No? Okay, whatever. It's just going to be unhappy. So we have a left position, we have a right position, we have siblings, we have children, but we don't actually have a way of storing any of this information yet. So what we want to do is do the positional binary tree. So we would use positions and nodes. So we're going to do both positions and nodes and follow that same idea where we can validate a position, we can validate a node. They all belong to us here. And we can kind of copy along. It fits relatively well with this one here. So we go to our trees and look at the implementing a tree. This is the linked structure. So again, this lovely little picture here. You have a parent, you have data, you have a left, and you have a right. So we can add a root to a tree. For an empty tree, we can add left, we can add right, we can replace, we can delete. Attaching trees is not all that interesting here, but right, once we have a tree, we can add a root to it for an empty tree. We can add left, we can add right. So first we'll start with that little node position, right, that has the data, has a parent, has a left and a right. So we're following the links here for these. So this will be our class for a linked binary tree. And we can extend binary tree here. Again, we'll try and follow on the inheritance example here. If it gets too confusing, let me know, but it sort of works out with this one. I feel like easier than the lists here. So we know we can have left and right and siblings and children. Some of them are defined, right? We can get height because we're a tree. We can get depth because we're a tree. We can get is empty. We can get is leaf, is root, sort of, but we can't iterate over our positions. We don't know the length yet. We don't know how to get the root. We don't know how to get the parent of a value here. So we have a position class that has the individual data itself here, right? The individual element of a tree, sure. All right, so for our linked binary tree then, we're going to have our class for, this is a node. And then the node class then had those values for parent, the data, the left, and the right. So in here, then we can have this init method that takes the data, the parent, the left, and the right. And this dot data is the data. I'm sorry, self dot data is the data. Self dot parent is the parent. Self dot left is the left. And self dot right is the right. Right, so we can follow those sort of links here as we go with that position. Now we can default them to none, which is pretty helpful, right? So if I don't know what they are, we can assume they're none. So if you don't have a parent, like if you're the actual root here, you have no parent, and a brand new tree has no children either. We can assume they're probably none until we tell them otherwise for these nodes here. Yeah, those are redundant, right? I thought so. That's our node class, right? That's all it is. It just holds onto that for us. Okay, and then we can have the position here extending the binary tree position. This is awful here, but you can do that. So we can write the class for position then that is specific to our position, binary tree dot position. Yeah. So slots are a way of actually making it use less memory. It's more of an advanced thing we kind of skipped over earlier on. So slots say the only thing you need to track here is this. You can have additional things that are being tracked. It's a weird thing, like how the Python object dictionary, we know all these things about all the objects we have in memory. Slots will kind of trim that down and say, no, you really don't need to care about all these other things. So it's like an optimization. So for our purposes, we don't care. Yeah. So our position class here then, we can have our init takes a container and a node. A container and the node. Same with our linked list here. So the self.container is the container, and the self.node is the node. Right? It's just gonna, this is the link, or this is the tree I belong to, and this is the node that I'm pointed at, and the node then has the data, the parent, and so on and so on. We can define data, return self.node.data, and then I think we had an equals and not equals, right? Define equals. Yeah, one of these. Same idea here, right? Because we can get to the same node from different positions, right? Whether or not we're starting off at the bottom of the tree or the top of the tree, right? As long as they're the same type and then our nodes are the same, we're okay for equals. And I think that was it for position there then. Yep, position's good. Now the validate helper method, again, same idea here with the same ones. We're just getting that node back out. Oh, do I have to copy all that? That's ugly. So this is a helper method then for validate a given position. We'll do it a little bit at a time, I guess. Raise a value error, sure, why not? And a type error, sure. Do a type error. If we're not the container, raise the value error. Sure, type error. And this is position. He loves to use P instead of position. I think it's easier to just type out position. But again, that's okay. And then if our parent is none, right, that's our convention for it's no longer valid, we'll raise the value error. So that's position again. So if our parent is ourself, we're pointing at ourself, back at ourselves, we're an invalid node. So parent being none is proper here because the root node will have no parent. So what we had done before with the invalid was if node doesn't have a next. Yes, you can add a root using the add root function. Yep. Yeah, we'll get to that in just a little bit. We're getting to those functions here. We're working our way down. Right, making a position then, right, from a given node is right, another helper method here. So given a node, I can make a position out. Those underscores don't seem to copyright. That's okay. So given a node, I can turn it into a position. Now this is just some fancy shorthand. We're going to say, okay, return self or a position of self as the container node if the node is not none. Otherwise, return a none. Right? It's the same thing as saying, hey, if node is none, return none. Otherwise, return self.position of self and node. Right? This sort of none there. Oh yeah. Same idea here. Right? They're just doing it all in one line. Is all. So he loves those one-liners. All right. Now we can finally start making our tree. Right. So when we make a brand new tree, we have no root. Right, and our size is 0. So we can define in the init self.root is none, and self.size is 0. Okay, now we have a tree. To return the length, right, that's just our self size. Yeah, that should probably be, these should be marked as private. You don't want people accessing these directly. So for defining our length, return self.size. For a root value, right, to get the root out, we'll give you a position of root. Right, so these are ways that you can get values out of the tree. Return self.makePosition of self.root. Right, so it might be none, and if you make position of none, you get none back out. But eventually we'll have one in here, so that we have root, and then we have left, parent, and right of positions. So define parent of a position, because this idea is people are going to interact with our class given the position. So we'll have the node is self.validate the position. Then we're going to return self.makePosition given the node.parent. Right? Go find the node's parent, turn that into a position, return it there. We can define left of a position. Same idea here, grab the node, return the node's left. Same with right. Define right, validate the position, return the node's right. Okay, so if you want the parent of a position, go validate it, get the node's parent. If you want the left, validate it, get the node's left. If you want the right, validate it, get the node's right. They're just quick, easy ways for us to get values back out. Now, number of children, this one's a little bit funny here, but it works out here. So we can define the number of children for a given position. Right, so we're going to assume it's 0. So children equals 0, and then if self.left of the position is not none, children plus equal 1. And then if self.right of the position is not none, children plus equal 1, return children. Right? If we have a left, add it. If we have a right, add it. Return that number of children. Maybe that should be number of children. I don't know. That should be fine. So we can figure out how many children we have from a given position. Sure. Adding a root here. Now this one is, notice, a private element or private function here, given some value. We'll go add this one here. So we want to define add root given some data. So we need to make a position, or see if we're not none, we already have a root, we can't do it. So it's a quick little sanity check. Otherwise, we can go through and make a position. Not as fun when I copy paste everything, I'm sorry. Here's the value error. Otherwise, all right, now we have one thing. We have a root, and we're going to make position of the root. There'll be a node. Our node class then, right? Underscore node has no parent, right? Because we're the root, we have no parent, we have no left, we have no right. So the only thing we have there then is the data. Node of our data. So again, that's a private method here. That's just a little helper method here for adding root. For adding left and adding right, same ideas. We need to validate, make sure they don't have a left child, add the node to the left, return its parent. We can define our add left of a position and the data. Right, first go validate it. Make sure it's a valid position. Validate the position. And then if node.leftChild is not none, raise a value error. You can't add a left child because you already have a left child. Right? Otherwise, then we'll take our self.size plus 1, and then we'll say node.left equals a self.node. Right? That its value is the data. Its parent then is the node. It has no left and right. Okay, we're going to add the node, and then we'll return the position of it here. Return self.makePosition of our node.left. Right, so this sets up node as the parent with having a left child. So our left child has a parent of us. Our left child has no other children, though. So we leave the left and right of it alone. And we'll do the same thing with add right. Add right, check the node right, take the node right, make position out of node right. We can add something to the right of a position. Then we can replace a position, right? We can delete a position, we can attach trees together. Goodness. So we did add left, let's do replace. So to replace a position, define replace position and the data. So we need to validate it first. Get the old data is the node.data. Take the node.data, set it to the new data, and return the old data. Right? As long as it's valid, we'll take it and return it. No problem. We'll go update all that. To delete a position, now this one is trickier. So deleting, if it has one child, great, we can delete, replace it with the child. If we have two children, we can't do it here, because we don't know which one's going to go there. So this is delete a position. We'll go validate it here. And then we can say, hey, if self dot number of children of the position is equal to 2, we'll raise a value error, right? Invalid, you can't do that sort of thing. Sorry, I'm getting itchy here. That's no good. Otherwise, then we need to find out which child are we going to replace it with. this is some crazy syntax, but we know if we have 0 or none, we'll say it's the left. If left, I mean, if it's not none, otherwise we can take the right, because I know I don't have 2, so I either have the left or the right. It could be none, right? So if it's none, then super easy, we're just done, right? I'm sorry, if it's not none. So if it's not none, then we're going to jump over us. We'll take our child's parent, becomes our parent. Take ourselves out of the list. If the node is the root here, then our child becomes the new root. Right, so if we are the root, our parent is going to be none, and then the child's parent now needs to be none, which is fine. We updated it, and then we'll say, okay, root is now the child. If we're not, then otherwise, now link it up with our parent. And then if it was our left here, if our node is our parent's left, right? So if we're the left child of our parent, then the parent's new left child needs to become our child. Otherwise, we must be the right child. So if we're not the parent's left, we must be the parent's right. So we're just fixing up our parent. So if we were the left or the right of our parent here, we're going to replace it with our child here. It could be none, right? Not a big deal here. It could be none. Then we'll take our size down by 1. Set our parent to none, to ourself, right? This is how we say we're no longer valid here, and return our data. So that deletes a position. What's wrong with that? Bad character. It must have copy pasted funny. So then we can return our data. So we can delete these values out then. Okay, and then attaching 2 trees. Again, this one's kind of boring here. Take a left tree and a right tree now and make them be our left child and right child. It only works if we don't have children. Right? If we're not a leaf, it doesn't work. I don't think we need to go over that one. It's probably okay. So all of this then should work now with our helper methods and the stuff we already have written. So our number of children we've defined of a given position, children of a position we've defined, positions we haven't done yet. So we need to still do that one. We have length now. Is root, is leaf, should work as long as we can return a root here. And I think we did that one right in our binary tree. We did a root here, right? It's make position of root. We did parent, we did left, we did right. We did number of children. We didn't do add root as a public function yet. Let's see, where do we have to do that one? That's the root position. I think we're missing part of it here. Where'd it go? So we don't have anything to actually do yet. So if you make our tree is a linked binary tree, tree dot. We can do the left, we can do the right, we can do parent of positions. We can get the number of children of a position. We can figure out if we're empty. We can get the children, figure out if it's a leaf position. The depth of a position is root height. We need the positions iterator. That's right. So we need the root. I think root will give us none. Yeah, make position of root. When we make position, we'll get back none. So we need a way to set the root value. Where are we missing that here? Was it in there? We're setting, this returns the root here. Make positions. I must have missed it. Oh, add root. Okay, yeah, so we missed these functions here. That's what it was. So these are the public ones here for add root, add left, add right, replace, delete, attach. That's what we never added in our base binary tree class here. That's right. Okay. Yeah, we missed. So those are supposed to be public. Why didn't it make them all private then? And we made them all private here. Yeah, these weren't like marked as private. I thought they did that as a reason. Non-public update methods. I'm forgetting here. Let's see. This is why copying out of this is obnoxious, but it's no fun anyway. Let's see. Properties, left, right. We did all those. All right, I guess we just need to make them not private. We'll just say add root, add left, add right, replace, delete. So I think that what he must have done is probably the complete section is a little bit later. I think you have the public method then calls the private one. So that way the public method always looks a certain way. I don't know, it's kind of silly. So we'll make the tree and then we'll ask for their name. I don't know, your name equals an input of what's your name. And then we can say tree.addRoot given your name. Right, and then we needed your father's name. Father's name is an input of what's your father's name. And then we'll take tree.add to the left of tree.root is the position, the father. And then we'll do the same with mother. Say mother and mother's name, tree root, and we'll add to the right here. Now, do those addings, do they return? Yeah, they return the position here. So this is, then we want to save this as father position. And then the mother position. And then we can get father's mother, father's father, father's mother, right? So we kind of repeat this again here for what is your father's name. And then we will add to the left of the father's position. Oh, my computer's freaking out. Come on, there we go. Add to the left of the father's position here. And add to the left, or to the, nope, father's mother. Father's mother name. So it'll be the father's position as the right of that. Be the mother. Oh, I typoed that one too. These words are losing all meaning here. And we don't need to change the mother's position. We just need to go add it here. We don't need to keep those positions right now. So then for the mother's position, we'll go do this. What is your mother's father's name and your mother's name? Take the mother's position, add to the left for the father, add to the right for the mother. So it should give you your mother's father goes to the left of the mother. Your mother's mother goes to the right of the mother. I think it works. Right? So we added you. We added your father to your left. We added your mother to your right. Then we kept your father's position that we just created. To your father's position, we added his father to the left and his mother to the right. And then for your mother's father, we added to the left of the mother, and the mother's mother, we added to the right of the mother. Building out a family tree. Good thing we didn't go another generation, because I would just lose it here. Okay? So really, there's not a whole lot of things we can do to print. We didn't do the iterator yet, did we? Because we haven't done the tree traversals. So we need to do tree traversals before we can actually iterate over them to make any sense of them here. So there's a couple different ways we can iterate over trees, which are really cool, once we have a tree that actually works here. We'll get back to this array one in a little bit. Don't worry too much about it right now. When we talk about heaps, we'll do this next chapter. And then for general trees as well, you can have n number of children, which is just like a list of children instead of just a left and a right. And that was the first kind of tree we talked about, was instead of a binary tree, it's just some number of children here. Each one of those is another with some number of children and some number of children. But tree traversals is the more interesting one here. You can do a pre-order traversal, you can do a post-order traversal, or an in-order traversal. So different ways of doing them, and they all will do things differently. So with a pre-ordered traversal, these are all recursive, is why we studied recursion first. So you're recursively visiting each position in the tree. So you're saying, okay, visit the position, and then for each child in your list of children, recurse. Start the pre-ordered traversal at that child. So what it does then is it goes to your child, and if it doesn't have any other children, goes to the next one. If it doesn't have any children, go to the next one. So what you'll get out then is, for each generation, it goes, starting at the first one, goes to the first child, gets all of its end children, and on and on and on. Once it goes out, it goes to the next child, the next child. So once you have a child with children, it will recurse on that one, to this one, and then this one, and then it will go to the next child in this generation, do all of its children, go to the next child in this generation, do all of its children, go back to that child. Just kind of a fun traversal. This is the pre-order traversal. So we can do a pre-order traversal of a given tree here. So we can write a function to find a pre-order traversal of a given tree. So to do that, we're just going to print tree.root.data. Print the data at the root of that tree. Then I want to say for child in tree, or tree.children, right, get all of its children out, recurse. Do the pre-order traversal of the child. Right, and because all of these things are trees themselves, right, when we get out our children here, I think we could get the left and the right. I think we had children up in this one, right? Yeah, children would give you the left and give you the right. Okay, so they give us positions. That's right, so we're using positions. So we just need .data. So this should be a position. So for a given position, we'll do the position.data. Position.data, tree of the children of the position. That's position. No, that's a position. We need the tree class. Shoot, we need the, excuse me, because we need the children out. I guess we need the tree. Oh, goodness. We want a tree and a position, I guess, because you can pre-order from anywhere. Hang on, I'm confused myself. I'm sorry. Yeah, just for each child, do the pre-order of the tree. Okay, of the tree and the position. That's right, you need both. Of the tree and the position. So print the position's data, and then the tree children of the position. Pre-order given the tree and the child. So we should be able to traverse our tree then, our tree here. We'll do a pre-order traversal of our tree given tree.root. Right, get the root position out and start doing this pre-order traversal. So we should get my name, and then we should get my father's name, and then father's father's father, mother. I'll go back and get my mother, and then print mother's mother, or mother's father, and mother's mother. Because it's doing this in order traversal, or I'm sorry, the pre-order traversal. So it's doing the level, and then going down to the child, doing that level, going down to the child. So it's going to drive all the way down. So if you imagine a really big tree here, right, a pre-order traversal is going to go all the way far down as it can first. You don't have to add make shell. You don't have to have children, right? So binary tree is 1, 0, 1, or 2 children here. So with whatever tree structure we had, right? Imagine now one of, say, like this one had another child here, which had another child over here, and this one had a child over here. This sort of thing. So the pre-order traversal is going to go to this one first, then it'll go to this one, then it'll go to this one, and then this one, and then this one, and then this one, and then this one. So it's going to start driving down as far as it can get on your left side before it ever goes to the right side. Then it'll come back to the right side once we've gone from here to the right side and go down, and then go to the child one here. We should be able to do our pre-order traversal. Let's see if it works here. So I'm Eric. Oh, goodness. Adding root failed. Where did that fail? Raise a value error is not none. What do you mean? Root was not none. Root was none. We tried adding root. Oh, root here is private root here under, and I had a non-private one. Self.root and self.size. Okay, let's try that. We have Eric, Gary, oh goodness. Self.private validate here. Private validate, this is, I copy pasted all of these, so now I have like, they're all wrong. There we go. And self.root underscore private root underscore private size. Oh no, we did a bad thing there. Yeah, we got size. Okay, I think we got it now. Let's try it. Eric, Gary, oh no. Position dot node. Position not have a node. Oh, position has, yeah, position has a node. Is position.node. Yeah, position has a node attribute. Here's getting this wrong here. So from, yeah, node should have parents. We're validating it. And in validate, the node's parent is the position. Oh, did I misspell parent? Is that what I did wrong? Parent, self.parent, parent, node's parent, position, node, self and node, should be fine. If the node is the positions node. What did we do wrong here? So we're trying to add left. So on adding left, we validate the position. And when we're validating the position, we got positions node's parent is invalid. Function given the position. Yeah, it's not liking position here from validate the position. Oh, we gave it the function add root here. So tree.root should have returned make position of self root. Oh, but was that was none, right? When we had a root there. We should have had a root. Tree.root. Okay, so let's add root here. So we'll say root is equal to add root. And we'll just use the root variable. Try one more time. Ah, no, okay. Still there, so our function tree, so adding root was failing. What was adding root giving us back? Adding root was returning the position, make position of self root, make position, so position, container in a node, should be fine, of our root. Self root is node of the data. All right, so let's put a breakpoint in here. Let's run it in debug. See why it's failing here. Capital P for position, yeah, it should matter because we have the capital P position class is self position here. I'm not sure. So we have self here. Let's see if we can add a root. So self is going to be, all right, here we have tree. Tree has a position. Tree has a root. The root is a node. Eric, yeah, that looks fine there. There's a node class. Yep, that's fine. Father's name, go to console. All right, let's step into our code here and see. So we're going to add left, given a position. So the position container has a node. We're going to validate the position. So let's step into validating the position. It is the right instance. Its container is self. Here, positions.node. So we don't have a node attribute is the problem. So, because because we inherited, we inherited from this other stupid position class, I think. Is that it? So we have a position node attribute. Why do we have a capital N? Position. We should just have a node attribute of position. Wonder because we're this type of position if it failed. It just has element. Position. So I think we messed something up with our position here. It didn't make the right position. Position. It's saying we don't have a node here of this position attribute. We should have a node. It has this node, but there's nothing, no value there. It has a root, not a node. I think when we made position, did we mess this up when we make a position? We need the container and the node. We have the container and the node when we made a position. I think something's wrong with this, is why. The root node, node class. Oh goodness. It's not like our position. Can we do this without the inheritance? I think we can do it without the inheritance. Try one more time without that. No, nope, okay, still failing. Making a position with the container and the node should just have position.node. Make position given the node of self root. Let's try and debug one more time, and if not, we'll call it quits and we can figure it out Thursday. All right, so self then is our linked binary tree. Good so far. Has a position class, has protected attributes, has the node class. Why doesn't it have the position class? We're make position, where node then is the node we just created. Node should have those attributes. Make the position given the container and the node. We have the container, don't have node. What is node here? It says node is a bound method. That's the problem. So it's not picking up the right node here. Self.node of the data. Self.node. Why did it not pick it up? So something's not creating that node right. I think that's the problem. Get rid of the data. Just get rid of this stupid underscore. Let's try that. Stop one more time. We have other, we just have positions. We don't have other nodes. One more run. This is data structures and algorithms in Python by Goodrich. Staggering. Eric. No, okay. I will have to figure this out on Thursday then. We're out of time. Why is it not validating right? Adding validates the position. It fails at validating the position. Position, self-position, container. Yeah, like it just doesn't have a node property. I think that's why it's confused. Data position, is container node. Yes, they make a similar book in all the different languages. This I think also had Weiss in Python and C++ and oh, this one's not Weiss, but it might be a similar book because we do it in Java, Python, and C++. All right, let's see, Eric. We're adding a root. I'm going to make a node here in a second. See if that works. So now we have a node. Yeah, node is not working here. That's the problem. So we have a root. Self-root. Oh, there. Okay, so now root has a value. So that is a proper node then, the node object. That's good. Oh, this is here. So I have self_root and not self_root. So self.root without the underscore is the function root. That was the whole problem. I think that's what it was. So you can self.root is the function root, not self._root, the attribute root here. Remember, if you don't put the parentheses, it's the definition of a function, not a function call. That's why we needed the root to be private. Eric. Oh, come on. Okay, so now none has no left. Okay, we're getting closer. We tried to validate the position, and it was none had no left. Okay, we're getting closer. Getting closer. We'll finish picking this up. Adding root on Thursday. Okay, folks. Adding root. Makes position of root. Make position. If node is not none, it shouldn't have been none. We just assigned it. I don't know. We'll pick it up on Thursday and debug it from there. All right, folks, you take care.